Hello everyone, I'm Gagan, a PhD student at Stony Brook University, working under the guidance of Professor Anshul Gandhi. Today I'll be talking about our work on detecting bottlenecks in microservices application using graph neural networks. This is a work done in collaboration with Anurag, Rohit, Bhargav, and my advisor Anshul. Microservices architecture is a style of architecture that allows an application to be decomposed into fine-grained, modular, and interacting services called microservices. This design allows independent development, maintenance, scaling, and fault isolation. Because of these advantages, microservices architecture is rapidly replacing monolithic or multi-tier architecture. Since the applications that are implemented by this architecture are usually customer-facing, maintaining performance is crucial. The images that you see represent different applications across different companies. The nodes in these images correspond to microservices and links correspond to an interaction between the microservices. Since the applications implemented using the microservices architecture are customer facing, it is important to detect and mitigate performance bottlenecks to provide good user experience. With microservices architecture, this task is hard because it's difficult to precisely pinpoint bottlenecks, although fault isolation is an advantage of it. There's also scarcity of labeled data in production systems to use data-driven approaches to understand the complex interactions between microservices. Additionally, the dynamic nature that we see in microservices applications due to software updates or components like cache, queuing, etc., which change the call graphs with time, the learned patterns cannot be generalized over time. So this begs the question, how to precisely pinpoint bottlenecks using limited label data in a generalizable way. We feel graph neural networks are the way to go about this. Let's briefly understand what are GNNs. GNNs are neural network models that learn representations on graph data via feature propagation and aggregation. Coming to the why, recent works show that GNNs provide superior performance on graph data. The way GNNs learn representation helps them understand the dependency among nodes. Recent works also show that GNNs are good at handling multi-class imbalance problem, which, as discussed, due to the unavailability of label data, persists in case of detecting bottlenecks in microservices application. The problem of generalization can be solved through transfer learning with respect to GNNs. System design, we divide the problem of detecting bottlenecks into two stages. The first stage being detecting anomalous traces. When I say anomalous traces, I mean these are traces that were affected by the existence of bottlenecks. For example, if there was interference, these were the traces that were collected during the period of interference. And the second stage of the problem is to detect bottlenecks in such potential anomalous traces. We transform the problem of detecting anomalous traces into a graph classification problem and transform the bottleneck detection problem into a node classification problem. The solution is also two-staged, similar to the division of the problem. We use hierarchical classification system because of many of its advantages. The advantages and few of the disadvantages are discussed in the paper. The architecture used for the stage 1 and the stage 2 are also shown here. The details of these layers and also the advantages of each layer is discussed in the paper. Coming to the dataset used, the dataset is from the firm paper that was published at OSDI in 2020. The dataset contains traces of social networking, media microservices, and hotel reservation application from the Death Star benchmark. It also contains traces from the train ticket application. Each trace consists of a single bottleneck that was induced through artificial interference. One of the main goals of this work is to understand how GNN-based models perform on an imbalanced dataset. To evaluate that, we randomly sample the original dataset to create three datasets A, B, and C. These are imbalanced datasets, and the percentage of traces that have bottlenecks are shown in the brackets. We evaluate the performance of MEG for all the four applications across the three datasets mentioned in the previous slide. We compare the performance of BMEG versus SVM, a model that was used in prior work to detect bottlenecks. The images that you see here are for the social networking application for 3 different datasets that I mentioned in the previous slide. The metrics that are used to evaluate the performance of BMEG and SVM are accuracy, precision, and recall. In the graphs, A stands for accuracy, NB stands for non-bottlenecked, and B stands for bottlenecked, P stands for precision, and R for recall. So NB and B are basically the 2 classes in the dataset. The metrics that are relevant to each graph are given over the image. Just to summarize the results, BMEG maintains good balance between precision and recall for complex call graphs, which are usually seen in the case in social networking application, even when the dataset is highly imbalanced. For simple graphs that are seen in media microservices, hotel reservation, and train ticket applications, SVM does perform better than BMEG as it's easy to learn thresholds and that differentiates bottlenecked and non-bottlenecked microservices. Moving on to the conclusion, the main conclusion of this work is that BMEG shows superior performance in detecting bottlenecks on imbalanced datasets for large and complex call graphs compared to SVM. This motivates us to explore the solution more. Coming to the future work, we want to explore how well GNS generalize by employing transfer learning. As already mentioned, the firm dataset contains single bottlenecks per traces. We also want to generate and open source a dataset with multiple bottlenecks per trace. We also want to analyze the impact of dataset size and performance and training effort. Lastly, we also want to compare our work against other related works and also industry standard tools like AppDynamics. Thank you.